outside, or kind of. It's just muggy now, so. Okay, so last Wednesday we were talking about this idea behind resonance structures, okay? So we had drawn kind of a questionable structure. We had drawn something called the allyl carbocation. And so when you draw the allyl carbocation, one way to draw it is like this, right? But we had gone through the whole idea behind molecular orbital theory, etc., explaining that this is not a satisfactory way to draw this, right? Or it's not explaining the entire story behind this allyl carbocation, okay? So the other side of this story is drawing its resonance structure, which looks something like this, okay? Okay, so this is a satisfactory way to depict the actual bonding that we see in this molecule. Okay, these two guys are what are called resonance structures. Resonance structures. And again, the reality behind this situation is not one or the other, but is instead what we get from the resonance hybrid, right? Which is like a 50% averaging of the two structures, which we have shown down here below, right? Okay, so this whole idea behind resonance is, again, taking this model that we have, these bond line structures, these Lewis structures, and still allowing us to utilize them even though they don't accurately explain bonding sometimes, okay? Resonance is going to help us do that. It's going to actually help us explain the real bonding that we see in a molecule, okay? Okay, so at the end of the class, I talked about resonance, and I talked about the more resonance structures that you can draw for a molecule, the more delocalized the charge, the delocalized the electrons, okay? So I'm going to briefly mention what that means. This delocalization of both electrons as well as charge, right? So if we went back to our allyl carbocation, and the first structure that I've drawn here, we have a pi bond between carbon 1 and carbon 2, right? In the second structure, we have that pi bond between carbon 2 and carbon 3, okay? In the reality of the structure, right, which is what we saw with molecular orbital theory, where are those pi electrons? Are they between carbon 1 and carbon 2? Or are they between carbon 2 and carbon 3? Or are they between all three of them?
Ideally, between all three of them.
Right, so in the real structure, with molecular orbital theory, these electrons are not between this guy and this guy. Instead, they are delocalized between all three atoms, or over all three atoms, okay? So this is what we mean by delocalization of electrons. Instead of being localized between two different guys, they're delocalized throughout the entire structure. On the other hand, if we had something, let's say, like this, just something like ethane, or ethene, this pi electron, or these pi electrons right here, are they delocalized, or are they specifically localized between those two carbons?
Specifically localized.
Right, so this guy, we have actual localization of electrons. They're here, they're between these two carbons, whereas in our resonance structures, we're delocalizing electrons throughout the entire structure. So that's good, right? It's always good to spread out negative charges throughout more things as possible. We're also spreading out the charge, right? So we had a positive charge on carbon 3 in the first structure. We had a positive charge on carbon 1 in the second structure. Where is that charge really at? Is it on carbon 1 or on carbon 3? Or is it on both of them? It's on both of them, right? So we're not only delocalizing electrons through all three carbons, we're also delocalizing that positive charge between two different carbons, okay? Again, delocalization of both electrons as well as charge is very stable for a molecule. So they like to do it if they can. And the more delocalized the electrons, the more delocalized the charge, the more stable the molecule overall, okay? So this ends up meaning, in terms of our resonance structures, is the more resonance structures you can draw, the more stable the molecule. Because again, that leads to more delocalization of charge, more stable molecule, okay? Okay, so that's the basic idea behind resonance, okay? So now we're gonna introduce you guys, because for me, it's like, oh, look, this is our allyl carbocation. Obviously, the other resonance structure is this guy, but how did I know that, right? How did I know that this is a resonance structure for this? Or how could I have drawn that just given one or the other, okay? So now what we're gonna do is we're gonna go in to learning how to draw resonance structures, okay? And being able to accurately assess whether or not a resonance structure is a valid structure and whether or not it is like a very contributing structure to the overall structure. Okay, so now how are we gonna do this? So the first thing we have to introduce you guys to before we can learn these various patterns of resonance is learning how to utilize curved arrows in resonance, okay? So I'm going to tell you what I mean by curved arrows. So curved arrows, what do I mean specifically? If we have an arrow, right, that is an arrow, okay? There are two parts to this arrow. There is what we call the head of the arrow. So this is our head, and there's what we call the tail, okay? We are going to utilize this curved arrow notation throughout the course, specifically when we actually deal with reactions and reaction mechanisms, okay? What this is supposed to be depicting is the movement of electrons. So the movement of electrons, okay? And the way it does that is that the tail of the curved arrow is going to specify where the electrons start at. So your tail is always going to start where your electrons start at. And the head of the arrow is where they're going to. Okay? So we're going to use this a lot. So it's important to start getting used to this curved arrow notation. Tail is where electrons start, head is where they're actually going to be going to. Now, again, this is supposed to be specifying the movement of electrons, except for when we use it in resonance. Okay, so in resonance, we're going to use this curved arrows to help us see the actual other resonance structures, but this is not supposed to be depicting movement of electrons. Because again, in resonance structures, it's not that electrons are moving from one place to the other, it's just that they're spread throughout the entire structure. Okay, so the one big difference here, we're going to use this curved arrow notation, but this is not going to depict the movement of electrons. It's just going to help us find the other structures that we're looking for. Okay, so just a model to help us see the various resonance structures for a given structure. Okay. Okay, so as an example, let's say I had my little allyl carbocation and I wanted to use my arrows to determine whether or not I have another resonance structure for this. Okay, so to do that, I would draw an arrow from my pi bond here going to make a bond over here. Okay, and so I'm going to explain every little bit and piece behind this. So if we imagine the structure, we've got a carbon here. It's got a double bond, as is to this other carbon, right? What is implied at this first carbon? At specifically this guy that we're not drawing. Hydrogens, right? So specifically, there's no charge to that molecule or that carbon. So there are two implied hydrogens here, okay? What about this carbon? Carbon 2 up here. How many implied hydrogens are in that carbon? So we have 1 because we've got a double bond here and a single bond. So we've got 1 here. And then on carbon 1 over here, how many implied hydrogens are there?
3.
There are, it's got a positive charge. 2, right. So we've got 1, 2. We have a carbocation, the positive formal charge on carbon. Okay? Now, if we take, let me erase this guy. If we take the electrons that are specifically in this pi bond, right, and we move them over and make up double bonds here, so we can go ahead and do that, what has specifically changed in this structure? So now we have a double bond. We still have this guy. We still have these two. Does this carbon have a positive formal charge anymore?
No.
No, right? But this guy over here now does, right? Because it only has 3 bonds to it at this point in time, okay? So we have taken the electrons that are in this double bond. Again, our tail is starting where they begin at, and the head is going where they're going to. They're specifically going in between this carbon and this carbon, and we get a double bond there, okay? I want to make note that you have to be very specific when you draw your arrows. I couldn't have said like that, or I couldn't have said like that. I had to be very specific in the fact that my electrons start here, and they specifically go to here. These things are going to be graded. You're drawing these arrows correctly, so you need to be very specific about where you're putting your electrons and where they are coming from, okay? Okay, so, yes?
And it's always that when you have a pi bond?
So we'll talk about that.
Okay.
Yeah. So there's going to be 5 patterns that we're going to introduce you to, and being able to determine whether or not there's a resonance structure that you can draw from a specific structure. Okay, but this is just getting the hang. This is just getting the hang of how we're going to find these using this curved arrow notation. Now, on the other hand, I have one resonance structure here. I have another here. I can use my curved arrows to draw the resonance structure for this guy as well, right? So whenever we draw resonance, it's not just going this way. I can also ask to draw the resonance structure going back. So I wanted to do that. I would take my arrow, right? I would start with my tail on my electrons where they're starting at, and I would put my head where they're going to. So on the way back, this double bond now goes back to here, and the positive charge goes over to the first carbon again, okay? So it's back and forth. Again, are they resonating? Are the electrons actually moving between these guys? Over here, and now they're over here, now they're over here, now they're over here? Is that what's happening? No. Again, this is our model. We're explaining the actual bonding. There is no movement of electrons. The reality is it is spread throughout the entire structure because both of these guys are contributing equally to the real actual structure. And that is not always the case with this, and I just want to make note of that. But we'll talk about when you can know whether or not that's the case. Okay, so that's the beginning, right? Curved arrows. So now we want to go over a few rules with respect to drawing and utilizing curved arrows and drawing resonance structures that you cannot break. Okay, so these are no-nos that you need to avoid as much as possible. Okay, so one thing about resonance, it's usually going to deal with lone pairs of electrons, okay, and pi bonds, right? So pi electrons and lone pairs are usually going to be how we determine whether or not we have resonance structures for a structure, okay? So it needs to be either lone pairs or pi bonds. You cannot break single bonds when you draw resonance structures. That is absolutely terrible. No, you can never do that, okay? So for example, right now I have a positive charge on this carbon, right? Again, what is the amount of hydrogens that are there on that carbon? Just one, because we have that carbocation. If I try to say, hey, I'm going to go in, I'm going to take the electrons that are in this bond, and I'm going to make a double bond between these guys, right? I would fill that positive charge. So this still had this guy, but what would I have done in the process? If I took the electrons that are in my sigma bond here, what does that do if I make another bond with those? It breaks that bond, right? So we cannot do that, right? You're not breaking single bonds. It's pi bonds or it's lone pairs of electrons, okay? You have to be careful with that when we deal with resonance. So this is a no-no. Okay, so can't break single bonds, so don't break single bonds. I will get mad and I'll probably draw unhappy faces on your paper. Number 2, other rules of drawing resonance structures of using these curved arrows. You cannot break the octet rule. And there are going to be 2 parts to this. I'm going to explain both of them, okay? So first rule that can't ever be broken is that anything in period 2, which is things like boron, carbon, nitrogen, oxygen, fluorine, they can never have more than 8 electrons. That's the octet rule, right? So you can never have more than 8. So for example, if I went in and I said, okay, I've got a lone pair of electrons on this oxygen, right? I'm going to take that lone pair of electrons and using my curved arrows, I'm going to make a double bond with this carbon. What's the problem with this at this point in time? If I wanted to draw the resultant structure, I would have a carbon with a hydrogen, and a hydrogen, and what would be the bond between the carbon and the oxygen at this point?
A double bond.
A double bond, right? So I took those electrons, I now made a double bond. I took one of those lone pairs, so now oxygen has a nice positive or a 0 formal charge, but what's the problem with the carbon? How many electrons does it have around it?
10.
It has 10. Can't do that, right? So you can see this nice and easy in this situation, right? Because you can count, 1, 2, you see the hydrogens there, so you see that it has 5 bonds around it, and that can't happen. But what if we were doing something like this, where I did the same exact thing? I took the lone pair of electrons, I took those guys, and I said, okay, I'm going to go and make a double bond here. Is it as obvious that I'm breaking this rule?
Yes.
Ideally, eventually, it will be as obvious, because you know this guy's got a hydrogen, this guy's got a hydrogen. So the resultant structure looks something like this, with, again, how many bonds around this carbon? 5, right? Yes, 10 electrons, 5 bonds. It's the same thing. You can't do that. But I just want to make you guys aware that this is harder to see than the original one. The original one drew the hydrogens. This one doesn't. So you just have to be careful that you're not giving carbon, oxygen, nitrogen more than 8 electrons.
So it's kind of like the resonant charges definitely come in.
Yes. Okay, so we can never exceed more than 8 electrons for those guys. We can be okay with less than. So that's why it's kind of hard to say you can't break the octet rule, because in some structures it's going to be okay for carbon and boron specifically. So I'll make note of that. Carbon and boron to have less than 8 electrons. Those will be okay. The other guys, nitrogen, oxygen, fluorine, will very, very, very rarely have less than 8 electrons and be okay. So yes for these guys, no for these guys on less than 8. And if it is less than 8, it's usually only to the point of 6 electrons. Okay? So for example, if I said, hey, I've got this molecule, I'm going to draw a resonance structure for it, and I take my little arrow and I start at the electrons that are in this pi bond, and I put them up on that oxygen, what does that give me in the overall resultant structure? So I had a carbon that had 8 electrons around it. I've now taken this bond, though, and I've put those electrons up here. So now carbon only has a single bond here. How many electrons does it have around it at this point in time?
6.
Just 6. That's fine. That means it has a positive formal charge. And by putting these electrons up on oxygen, that gives it a minus formal charge. This is an okay resonance structure, even though it does break the octet rule by giving carbon only 6 electrons. Okay, this is acceptable. Can't ever have more than 8, though. Ever. It's bad. Just as a note, for this guy, we had what type of formal charge for the entire molecule here?
No charge.
0, right? We did introduce formal charge when we drew this resonance structure, but what did they sum to overall?
No charge.
0, right? So that's a big indicator too. Whatever the charge is on the original molecule, the formal charges that you may introduce have to sum to that exact same charge overall.
And as far as stability, this is more stable.
We'll talk about, yeah. So we'll talk about stability at the end when we learn our patterns. But yes, this is more stable. Okay, so those are the rules. Can't break single bonds. You can never exceed 8 electrons for those second row elements, but you can sometimes have less than 8 electrons when we are drawing these resonance structures. Now, the last little thing I want to mention is formal charge. Okay, so I did just note that this guy was 0. When we introduced formal charge, it summed to the same amount. But when you guys are drawing these resonance structures, you have to draw your structures with formal charge actually announced, right? So we talked earlier about these bond line structures, how sometimes they'll have lone pairs of electrons, but what must they always have if it's there? You always have to draw formal charge, right? So that's the number one guarantee. Maybe you won't see the lone pairs, but you will see the formal charge regardless. So let's say I had a structure like this, and I was going to draw a resonance structure for this. So I was like, okay, I'm going to go in, I'm going to take the electrons that are in this lone pair, and I'm going to make a bond between oxygen and carbon. What's now the problem if I do that with this carbon? If I take these electrons and I make a double bond here?
Carbon has 5.
Carbon would have 5 bonds around it. I can't do that, right, because I can't exceed 8 electrons. So now what's going to happen is the electrons that are in this bond, this pi bond, are going to go and they're going to end up on this carbon, okay? So the resultant structure, if we drew our little resonance arrow, would look something like this, right? So this would be the resultant resonance structure for that. We have now a double bond between carbon and oxygen, and we have put a lone pair of electrons on this carbon. Are there formal charges that I have to depict in this structure at this point?
Yeah.
Yes, right? So right now, we have oxygen with 3 bonds and a lone pair. So what is the formal charge there?
Negative.
3 bonds and a lone pair is
That's positive.
positive, right? So we get a positive formal charge on oxygen up here. Now what about carbon, who has 1, 2, 3, an implied hydrogen and a lone pair?
That's negative charge.
It's a negative charge, right? So now when I've drawn this, I have to explicitly say, this guy's got a positive charge, this guy's got a negative charge. It's part of drawing the resonance structures, okay? Again though, this is 0. When we sum these, what do we get? 0. Okay, so you can't introduce a new charge, right? That doesn't happen. They still have to sum to the overall one, but when you're drawing these, you do have to draw those charges on. Yes?
You only do one other one, or can you do more?
So we'll get through it. Let me go through the patterns, and then we'll talk about how to know like when to stop. Yep.
Why couldn't you have gone backwards?
You can go backwards
Like from the carbon to the oxygen, give it a double bond, and
from this structure.
yeah, and leave the you see what I'm saying?
So you want me to take this lone pair and put it back here?
Yeah, so originally, when there was a double bond,
Yeah.
couldn't you have just given it to the oxygen and give it a double bond?
What would you give it? So if you gave this bond here, then how many electrons would oxygen
Well,
have?
then you move one of the lone pairs from there.
Oh, that's
It's still the same thing. How many hydrogens does this guy have on the end? Hydrogen, hydrogen, hydrogen. If I took this guy here and took this guy here, I would end up with 10 electrons on this carbon up here, which was bad, and you can't do. So it's hard at this point because you guys don't know the patterns, and I do, and I'm like, oh, you take this and you do this,
Where'd you
right?
get it?
So yeah, it's easy for me to be like, this is what you do. It's hard to see what you can't do, but in the next slide, I'm going to teach you guys the patterns of drawing these resonance structures. Okay, so again, when you do introduce formal charge, which you will sometimes, you need to depict that formal charge. Okay, so now, these patterns. What are these patterns, okay? I'm going to introduce you guys to 5 of them, because that's what the book introduces you to. 4 of them are actually going to contribute to something, okay? So we're going to talk about 4 of them a lot, and the other one, not so much. But before we do, I do have to define a few positions in our structures, okay? So I've been talking about this allyl carbocation, right? So in our allyl carbocation, this was it, right? And did I ever define what the allyl position was, the allylic position? No. So now I'm going to define what that is, because that position actually plays an important role in our patterns for resonance structures, okay? So anytime we have a double bond, right, so carbon-carbon double bond, there are 2 important positions with respect to that double bond. There's something called the vinyl position. So this guy down here is vinyl. And there's something called the allyl position, okay? So when we abbreviate these guys, we call this vinylic, and we call it allylic. So you're going to hear me say the word allylic all the time because it pops up forever. Allylic. Okay, so what are they? So the vinyl position is the actual carbons that take part in the double bond. They are the sp2 hybridized carbons that participate in the formation of that pi bond. That's the vinyl carbons, okay? The allylic carbons, on the other hand, are the ones that are directly adjacent. Okay, so for example, in this molecule, adjacent carbons are here, 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 and here. They're this position that's directly adjacent to the double bond. This is all of these allylic positions, okay? the allylic position is going to play an important role in determining whether or not there are resonance structures. So that's why we introduce it. It's always going to be the position directly adjacent to the double bond. Okay, so now, what are these 5 patterns? So the first one we'll cover is allylic lone pairs. So lone pairs in the allylic position. The second is allylic positive charge. The third is a lone pair adjacent to a positive charge. The fourth is a pi bond between 2 atoms of very different electronegativities. And then the fifth is conjugated pi bonds in a ring, which again is not going to be super important. But we're going to walk through all of these and how to draw the resonance structures from them. We're going to start with allylic lone pairs, okay? Okay, so what do we mean by this? Allylic lone pairs. So for example, if I look at my first little structure here, and I want to draw a resonance structure for this, I'm looking for the allylic position, right? So first off, we've got this position, we have a double bond, right? What are those 2 carbons called? They're not allylic, but they are vinyl positions, so they're vinylic positions, right? Do I have an allylic carbon?
Yes.
Yes, right? So these guys are my vinyl positions. My allylic position is out here, this guy, right? Is there a lone pair of electrons in the allylic position?
Yes.
Yes, okay? So if there is, you have a double bond, you have a lone pair of electrons in this allylic position. The resonance pattern for this is going to start with the lone pair of electrons. So your tail will be on the lone pair. It's going to go and form a bond between the carbon that it's based on and the next carbon. Again, if I form a double bond here, what's going to happen with this carbon? It has way too many electrons. As is right now, there's a hydrogen here. If I form a double bond between this guy and this guy, I can't have this double bond here anymore, right? So what's going to happen to it? These electrons are going to go and end up on this last carbon. So we have a double bond forming here, and now we have a lone pair of electrons in this final carbon over here. Does this now have a formal charge? Because again, up here we had hydrogen, hydrogen.
Right.
We still have those hydrogens.
Negative.
2 of them. We've got 3 bonds in a lone pair, so what is the formal charge in this carbon?
Negative.
Negative. So that's the first pattern, right? We had lone pair of electrons in the allylic position. We use 1 arrow to form a new pi bond, and we use another arrow to move a pi bond to make a lone pair, okay? Notice that essentially we had a negative charge, and we pushed it all the way to the other side of the molecule, where we still have that negative charge overall. How many arrows did that require? 2, right? Why? Why couldn't we just use 1 arrow? What did we run into when we had this guy?
You would give middle carbon more.
Right? He couldn't break the octet rule. So if we had just done this with 1 arrow, this guy would have had 10 electrons, so we had to do it with 2. Okay? So 2 arrows for the entire structure. Okay, so same thing this next one. The only difference is, and this is what I want to make note of, technically, this oxygen here is what we would call our allylic position, right? We've got our double bond, and directly adjacent we have this oxygen, right? It's technically not allylic because it's not carbon. Allylic technically has to be carbon in this position, but it's oxygen and it's a lone pair, so we still call it the allylic position. I just want to make note of that if anyone ever tells you otherwise. But again, what we're looking for, lone pair in this allylic position. Do we have a lone pair of electrons in this allylic position? So allylic position is that this oxygen, is there a lone pair of electrons
Yes.
on it? Yes, right? So it's the same exact thing. Our arrow is going to start on that lone pair. It's going to form a double bond between whatever that lone pair is on and the next atom. As a result of that, though, what do I need to do to this pi bond, this double bond?
Move that pi bond to the left.
Right, so this guy has to go over here. Okay, so again, same thing, 2 arrows. What is our resultant structure? We get a double bond. We still have a lone pair up here on the oxygen. And now we have a lone pair down here. Have we introduced formal charge in this?
Not yet. You need to.
It's there, though. I haven't drawn it. Who has a positive formal charge now?
Oxygen.
So oxygen has a positive formal charge. Who has a negative formal charge?
The carbon with the lone pairs.
Right, carbon with the lone pairs down here. So again, 2 arrows. Right, starts where the lone pair is at, forms a double bond, and then it moves the electrons in that pi bond to a corresponding atom. Okay. So let's do one more. I have lots of these, but let's do one more. So we'll go over here to this guy. Again, nitrogen. It's technically not allylic because this nitrogen-carbon double bond, this technically doesn't define an allylic position. But again, it's a double bond, and you have a lone pair of electrons directly adjacent to a double bond, right? So where am I going to start my arrow here?
With the double bond?
With the double bond or with the lone pairs of electrons, right? So for these guys, it's always going to start with the lone pair. I'm going to take that lone pair. I'm going to make a double bond. But then what do I have to do to the electrons that are in this bond here?
I'd assume you take the pi bond and give lone pairs to them.
Right, so then I'm going to take the electrons that are in this pi bond, I'm going to put them on nitrogen. And so my resultant structure looked something like this. And a double bond. Do we have formal charge in this structure now?
No?
There was a negative here, right? We have taken that negative and we've pushed it up where? To the nitrogen. So that's one thing with resonance, right? If it starts here, wherever we push it to, if it's a negative or a positive charge, it's going to go to that position, right? Nitrogen now has 2 lone pairs and 2 bonds. This is a -1 formal charge. And we did that by pushing that negative charge up to the nitrogen. Yes?
Why did you give nitrogen 2 pairs of lone pairs if it was just 1 bond?
So again, this is like when we say, hey, we're not always going to give you the lone pairs. There was an implied lone pair on nitrogen.
Okay.
If there wasn't, it would have had a formal charge. But it didn't, so there was an implied lone pair. Okay, so that is the lone pair of electrons in the allylic position. How many arrows do you need to complete this pattern? 2, right? 2. Okay, so now, that's the first pattern. The second pattern, again, deals with that allylic position, but now we're going to be dealing with an allylic positive charge. So a positive charge in the allylic position. So we go back, we look at our 2 atoms that form the vinyl positions. If we look over into the allylic position, instead of having a lone pair for this guy, we have a positive charge. Okay, so this is the second pattern. When you have a positive charge in the allylic position. So now, what's going to happen here is we're going to start our arrow at the pi bond. Okay, so our arrow is going to start at the pi bond. It's going to move these pi electrons over to this guy. All right, so they were in between carbons 2 and carbon 3. Now they're in between carbon 1 and carbon 2. So when we draw our little resonance arrow and the resultant structure, we end up with a double bond between carbons 1 and carbon 2. Where does that positive charge go? Where does that hole go?
Third carbon.
Third carbon, right? And again, we can draw that by drawing out the hydrogens. If we take away a bond here, that carbon is going to end up with a positive formal charge. So that is positive charge in the allylic position. How many arrows did I need to draw the new structure? Just 1 arrow, right? And it's the arrow starting at the pi bond and going to the positive charge. So 1 arrow. Okay, so what about down here? If we look at this structure, do we have a positive charge in the allylic position? Yes, right? So we have double bond. We've got a positive charge directly adjacent to that. So with this guy, we can do the same thing. 1 arrow. I'm going to stop there, though, right? And I'm going to draw the resultant structure because of that. So we have 2 peaks and a half. Now we have a double bond here. We still have a double bond here. Where's the positive charge at? If I say 1, 2, 3, 4, 5, 6, where does the positive charge go for this structure?
On the 3rd carbon.
On the 3rd carbon, right? Positive charge, carbocation. Do we again have a positive charge in the allylic position.
Yes.
Yes, so now, same exact thing, one arrow. We can take this pi bond, put our little resonance arrow out, and we are left, that's ugly, 1, 2, 3, 4, 5. We're left with a double bond. We're left with a double bond. Now where does that positive charge end up at?
It's 5.
Position 5. Right, so notice we did get more than one structure out of this. I did not draw them all at the same time, and I would always recommend not drawing different resonance structures at the same time. Right, try to draw one arrow at a time to get a new resonance structure overall. This guy and this guy. Okay, so that is positive charge in the allylic position. The third one is a lone pair directly adjacent to a positive charge. So for this guy, we have two positions that are important. We've got our positive charge, and we have a lone pair of electrons that is directly adjacent to that positive charge. Okay, so this one is going to start with our arrow at the lone pair. It's going to go and form a double bond. And we get our resonance structure as a result that looks something like this. We did have formal charge. Do we have formal charge in the resultant structure?
No.
No, right? So again, for this guy, we have a lone pair of electrons directly adjacent to a positive charge. How many arrows do we need to draw to get to our new resonance structure? Just one, right? And where do they start at? Start at a lone pair, and they make a pi bond with that, okay? So one arrow here as well. Okay, so now let's go ahead. We're going to try some of these using the first three patterns because they heavily. Okay, so we're doing a couple of examples here. We have 3 different patterns that we've introduced thus far, and we're looking to draw resonance structures of whatever molecule we're given those 3 patterns, right? So I've asked you specifically in this question to locate the lone pair adjacent to a positive charge and draw the resonance structure. So both of these guys are going to use our pattern 3, which is lone pair adjacent to positive charge to a positive charge, right? If we look at the structure number 1, or A, we'll call this A, I don't see any lone pairs, right? But again, they're implicit in the structure. If nitrogen only has 3 bonds and it's neutral, it's 0 charge, then that means there is one lone pair here on nitrogen. And again, that is adjacent to our positive charge, right? So positive charge is here. So the pattern uses one arrow, and that one arrow is going to take the electrons that are in that lone pair, and it's going to form a double bond between the nitrogen and the carbon of the positive charge. So we can go ahead and draw our little resonance arrows. We end up with nitrogen here, positive. This is going to have a double bond, right? And now that positive charge, that hole, is essentially going to be filled by the electrons that we've taken here, right, by these guys. But because of that, we're going to leave that hole, we're going to move that hole to this nitrogen, right? And so this is one of our structures, or this is a resonance structure for this molecule. Okay, so same thing, and we'll call this guy B, right? So same thing, we've got nitrogen here. Nitrogen at this point only has 2 bonds. It has a negative formal charge, so we should be able to utilize that to figure out, oh, there are 2 lone pairs of electrons on this nitrogen. Same thing, we have a lone pair directly adjacent to our positive charge here. So we're going to take the electrons in that lone pair, and we're going to form a double bond between the atom that has the lone pair and the positive charge. So when we do this guy, nitrogen out here, we have a double bond now that has filled our hole here, which is good. There's still another lone pair, and there is no formal charge, right? So we essentially took the negative and we combined it with the positive to to form 0 overall. And you don't necessarily have to know the negative and positive, like as long as you can track the electrons and show, oh, the double bonds moved here, now we have only one lone pair left up here, then you should be able to see that everyone has a 0 formal charge, just by calculating formal charge like we have normally done. Okay, so I did put this slide in, and I'm just going to go over it briefly, right? So we're talking about our resonance pattern where we have a lone pair that is adjacent to a positive charge, right? And so for the ones that we've looked at thus far, these guys have only used one arrow to draw our resonance structure. And I'm going to introduce you to one little exception to that rule, and it's this functional group. This is called the Nitro functional group, okay? Okay, so again, if we look at this guy, it follows our pattern or falls into it where we have a lone pair of electrons, right? And it's directly adjacent to a positive charge. So ideally, we could say, okay, well, the electrons that are in this lone pair are going to go, and they're going to form a double bond in between the atom that had the lone pair and the atom directly adjacent to it, right? And so we could do that, and we could draw a new structure where we have a double bond here. We've got 2, but the problem with that at this point, if we only use one arrow, is that nitrogen would now have more than 8 electrons, which we can't have around it, right? And so this is the one exception. So we have one arrow that's going to make the bond between oxygen and nitrogen, but to make sure that we don't break the octet rule, we've got to take the electrons that are in this double bond and put them on the other oxygen, right? And so with that, this guy looks like this. We've got a lone pair. That negative charge is essentially moved from this guy to this guy, and we still have this positive charge on nitrogen, okay? So this nitro group is the exception to our pattern where we only need one arrow for this lone pair adjacent to a positive charge. It's not super important, that's why I didn't really mention it in class, but just so that you know. But the third edition does not talk about the nitro group, so we're going to be fine by skipping that slide. Okay, so the fourth pattern is when you have a pi bond between 2 atoms of very different electronegativities, okay? A good example of that is our little structure here. So we've got a pi bond between carbon and oxygen, okay? Do carbon and oxygen have different or drastically different electronegativities?
Yes.
Yes, right? So carbon and oxygen differ dramatically with respect to electronegativity. Who is more electronegative?
Oxygen.
Oxygen, okay? So in this type of pattern, you've got 2 different atoms with different electronegativities. What's going to happen is the more electronegative atom, who is oxygen here, this is more electronegative, is essentially just going to take the electrons in that pi bond. All right, so we're going to say, okay, the electrons start in our pi bond, but they're just going to go up to oxygen, right? And so we're going to end up with a carbon that has only a single bond, a new lone pair of electrons on oxygen, and what have we introduced to this structure?
Charges.
We've introduced formal charge. Now we have a negative charge on oxygen and a positive charge on the carbon. So that happens between carbon and oxygen. You will also see the same thing between carbon and nitrogen. Okay, so again, nitrogen is more electronegative, right? So we're going to take the electrons that are in this pi bond, we're going to put them on that nitrogen. We're going to end up with a single bond here. We now have 2 lone pairs on nitrogen in this other bond. So what is the formal charge on this carbon down here?
Carbon's gonna have a negative.
So carbon, we just took an electron from it. So carbon's going to be a positive down here. We'll introduce a positive formal charge here. And then the nitrogen's going to have a negative formal charge. Okay, so that is the last main pattern. Again, how many electrons or how many arrows do we use for this guy? This only had 1 arrow. And it started at the pi bond and it went to an atom, okay, as opposed to the reverse of that, which is essentially what we did with number 3. Okay, so then finally, we don't talk about this as much, but if you have a ring system, like we do in this nice aromatic group in this benzene ring, and this ring system has these adjacent double bonds throughout it, then you can see these electrons in this ring system be delocalized throughout the entire system, right? So, for example, say we have carbon 1, 2, 3, 4, 5, 6. All of these lone pairs, we can draw another resonance structure, not all these lone pairs. We can draw another resonance structure for this guy by just moving the electrons that are in all these pi bonds, and we end up with a new structure. Again, this doesn't come in really ever until second semester with respect to looking at resonance in these ring type systems. Okay, so now let's go ahead. We're going to try some. We're going to utilize all of them, right? Not except for number 5 because I don't really deal with it too much. But we have 4 different patterns, and I want you guys, I have 3 molecules, and I want you, well, this is summary. This is a nice summary slide. Okay, so you guys did this one in class. I gave you 3 different structures, and I wanted you to draw all of the possible resonance structures from them. So for example, for number 1, I don't know if I have enough room. Maybe I'll draw it down here. So for number 1, I also instructed you, just as a good rule of thumb, to start using the patterns with only 1 arrow first and then move on to 2 arrows. And so for this guy, the first thing I would do is look at this and say, okay, do I have any lone pairs that aren't being shown? There are 2 lone pairs that are on this oxygen. And so with that, I say, okay, what pattern can I see, right? And so if I look at my double bonds, I don't have anything in an allylic position, right? So I don't have an allylic lone pair. I don't have an allylic positive charge. I don't have charges being separated. I don't have a positive charge adjacent to a negative charge. What I do have, though, is I have 2 atoms with different electronegativities. So I have an oxygen, which is very electronegative, separated from carbon via a pi bond, right? So what's going to happen first in this guy is when I use our pattern with 1 arrow, I'm going to take the electrons that are in that pi bond, and they're going to go up to the oxygen. And that's a really ugly arrow, so I'm going to go ahead and do this guy. And I'm going to specifically say these electrons that are in this pi bond are going up, and they're going to be on oxygen in my new structure. And so then I can connect this with my little resonance arrow. So now that pi bond, that double bond, is now just going to be a single bond. We've got oxygen, and now it has 1, 2, 3, 4, 5, 6 lone electrons. We still have a double bond over here, but in taking those electrons from that pi bond, we have left behind a positive formal charge on carbon, on that carbon that we took them from, and now we have a negative formal charge on the oxygen, okay? Okay, so that first pattern was pattern 4. This is atoms with differing electronegativities. All right, so we have an oxygen, a carbon, and we have a pi bond between them. I should say that, pi bond. I don't like to write things out, so. With electronegativities and pi bond. Okay, so now we have this structure. We're here. And now the question is, well, is there anything else? Can I draw anything else, right? Are we seeing any of the other patterns that we are trying to learn? And so hopefully you can see that we've got a double bond over here, and we've got a positive charge in an allylic position from that double bond, right? So this is going to be pattern number 2, which is the allylic positive charge. I'm going to take the electrons that are in this pi bond, and I'm going to put them in between these 2 carbons, right? So then we draw our new structure where we have a single bond, a double bond, and be more firm with the double bond, and we've got our lone pair of electrons on the oxygen. Now that positive charge has moved from this carbon, and it has moved to this carbon, the end carbon out here. Okay, so for this guy, we had 3 resonance structures that we could draw that would satisfy the original molecule. Okay, so then let's move on. That's number 1. We'll go on to number 2. So again, the first thing I try to do is identify any type of lone pairs of electrons. There are lone pairs on this oxygen, right? So at this point, I've got a lone pair directly adjacent to a positive charge. So this is our pattern 3. So I'm going to take the electrons of that lone pair, I'm going to go and I'm going to form a double bond here. And so the only thing that we get out of this is that double bond, right? That's going to fill the hole that was on this carbon. We're going to take those electrons, fill that hole. That means that that positive charge is going to move up to the oxygen. And we can see that just in the resultant structure. We have an oxygen with 3 bonds and 1 lone pair. And so that is it for this guy. There's only 2 structures, and it followed pattern 3. And then finally, we'll go on to number 3. I'm going to redraw this guy down here. We've got a positive charge and 2 double bonds. So this is the original structure. I'm going to go ahead and label these carbons. We've got 1, 2, 3, 4, 5. Okay, so if we look at this, the first thing that we can see, ideally, is that we have a positive charge, and it is in an allylic position, period. Right? So positive charge in the allylic position. So we're going to use that same pattern where we take the electrons of the double bond. We go and form a double bond over here. So we've got a double bond. We still have our double bond over here. Now that positive charge has gone from carbon 1 to carbon 3. All right, we've taken the electrons here, we've moved them in between carbon 1 and carbon 2, and so now that positive charge lies on carbon 3. We are still in the exact same position that we were, though. Now we still have a positive charge that's in an allylic position. So the next step that we're going to do is we're going to take those electrons on this guy, we're going to move them here, and we're going to be left with a double bond. We're going to be left with a double bond, and now we end up with a positive charge on that 5th carbon on the end. So again, we could have done that in theory all in one step, but you always want to follow single arrows first to find all of the resonance structures. Okay, so that is that, right? So if I ask you, draw all the resonance structures, this is what you would do. You would start ideally with single arrow patterns first, and then see what kind of develops from that. Again, going back to utilizing our patterns for drawing these guys. Okay, so at this last part, I'm going to just briefly go over how to know. Number one, like, we can draw all of these resonance structures, right? There's certain molecules that you can draw quite a few different resonance structures for. The first question we have to ask, though, are all of them contributing to the real actual structure, right? So which are actually going to be contributing resonance structures? And then number 2, we can also ask, if they're not equivalent, who's contributing the most? Like, who does the real structure actually look more like, right? So what I mean by that, I'm going to use our allylic carbocation as an example. So we had introduced all of this resonance with this guy, where we had this carbocation, and it was in the allylic position. And we now know that we can draw a resonance structure from this, right? We can take the electrons that are in this pi bond, we can move them in between carbon 1 and carbon 2, and we get this guy with our positive charge moving over here, right? So these are our 2 resonance structures to represent the actual structure of this molecule, right? Both of these guys are what we would call equivalent, meaning that they don't differ, right? They have a positive charge, they have a double bond, so both of these guys are equivalent to one another. Because of that, both of them are going to contribute equally to the real overall resonance hybrid, right? So we drew this resonance hybrid as being the average of these guys, right? And we said, oh, we've got a partial positive, and we've got like a bond and a half between all the carbons, okay? This was our hybrid. Okay, so this guy, because of that, because they're equivalent, they equally contribute about 50% and 50%, okay? Now, that's not always the case, that we have equivalent resonance structures and they're going to essentially contribute the exact same amount, or they're going to contribute equal amounts to the overall structure. So for example, let's move over here to acetate, and let's draw all the resonance structures that we can for, not acetate, but this is acetic acid. So the first step I'm going to do, I'm going to draw in my lone pairs of electrons. So note that in this structure, I could use my first pattern. My first pattern was lone pair, allylic to a double bond, right, in the allylic position. And so with that, I would use 2 arrows, right? I'd say, okay, I'm going to take the lone pair of electrons here, I'm going to make a double bond, but I can't break the octet rule with this carbon, so because of that, these electrons are going to go and end up on the oxygen, right? This guy utilized a 2-arrow pattern. I don't want to do that first, though, right? So again, I always say use the patterns with 1 arrows first, right? And so because of that, I'm not going to go that route originally. Instead, what I'm going to do is I'm going to use pattern 4. So pattern 4 is the atoms with differing electronegativities, and there's a pi bond between them. And so with that, I'm going to take the electrons that are in that pi bond, I'm going to put them on oxygen, and my first resonance structure for this guy is going to have a single bond, and it's going to have 3 lone pairs around oxygen. So I've introduced a negative charge to oxygen, I've introduced a positive charge to this carbon down here. Now, second, we've got a lone pair of electrons directly adjacent to a positive charge, so we can draw another structure where these guys go and form a double bond, and we end up with something that looks like this. I wish I wouldn't get so small. Okay, hold on. I'm going to draw this a little bit better. So we get this guy, he's here, we've got a double bond, we've got a lone pair, and we've got this guy with a couple lone pairs up here, and that positive charge has moved from the carbon that it was on to the oxygen where those electrons came from, okay? So overall, we get 3 different resonance structures, okay? Now, the question is, comparatively to our allylic carbocation over here, are either of these structures, or is somebody of these 3 structures going to be more significant than the others, okay? And so the answer to that is yes. And the one that is the most significant is going to be this first structure, right? I'm going to say, I'm going to estimate maybe that this first structure is maybe like 90% of the actual structure of acetic acid, right? The other 2, we'll say, are their remaining 10%, okay? Now, how do I know that? Well, there's a few different key things that go into determining who's the most significant structure. And the first number 1 thing is formal charge, right? In our first structure, there is no formal charge, right? That, if there's no formal charge, is always going to be the best structure, the most significant structure, right? So for this guy, this is most significant, right? And it will contribute about 90% of its character to the overall structure, okay? Now, if we do have to introduce a formal charge, we really want it to be low, right? So we don't ever really want to move past maybe 2 formal charges, and I'm going to talk about that in a second, right? So maybe a negative and a plus. And we never want to go past -1 or -2, or no, pardon me. We never want to go past a 1 charge, right? We never want to see like a -2 or a +2. These are bad, right? So though if you ever had a structure that had this, they would not contribute to the overall structure, right? So at most 2 formal charges. We want to keep them at just a minus and a +1, right? And then if we are putting on formal charges, we want to put the negatives on the most electronegative elements, and we want to put the positives on the least electronegative elements, right? And so if we look at the 2 other structures and we say, well, who is more significant, right? Structure, we'll call this guy 2, we'll call this guy 3. We'll notice that on structure 2, we've got the negative on oxygen, which is the more electronegative element, which is good. On 3, we also have the negative on oxygen, which is the same, so we can't utilize those to differentiate. But then if we look at the positive, in structure 2, we've got the positive on carbon. In structure 3, we've got the positive on oxygens, right? So if we're going to put the positive charge on the least electronegative element, ideally that would go in the carbon, which is in structure 2. So we think, oh, structure 2 is going to be more significant than structure 3. That would be true as long as our other little qualifying factor wasn't different between the 2, right? So then we always want to complete octets, right? So in structure 2, carbon, this guy right here, does not have an octet. Does not have And octet, right, it only has 6 electrons. In this guy, everyone has an octet. And you can go through and count those if you'd like to. So even though in structure 3, the positive is on oxygen and not on carbon, structure 3 is still the more significant of the two because everyone has an octet. Significant. So then if we were going to label these, we'd say this guy is structure 1, this guy is structure 2, this guy is structure 3, and we wanted to say rank them in order of, let's say, increasing significance to the overall structure. We would say, okay, the least significant is structure 2. It's going to be less than the second most or second least, which is structure 3, which is always going to be less than structure 1, which is the most significant. All right. And again, if we wanted to kind of divide the percentage up here, we'd say probably this guy is like 7 and this guy is maybe like 3, right? And I'm making those percentages up. It's just trying to give you an idea that, you know, if you really think about the actual structure of this molecule, we can consider it about 90% of the time to look like this. The other 10%, maybe it has some character here, 3% there, and then the other like 7%, maybe it has some character here, right? So all of these go into form it. It's just who's actually going to represent the actual structure the best, I guess. Okay, so those are two different things, formal charges and then complete octets. Okay, so we can do the same thing for this guy. So this is exactly the same as we just saw, but this is the acetate ion. So for example, we just drew the resonance structures for acetic acid, which is this. The only way this guy differs is there is a lack of a proton on this terminal oxygen, right? So you would think, oh, well, if we draw the resonance structures for this, it's going to be really similar to the resonance structures for what we just drew, acetic acid. So if we start this, you could think that, but you would actually be wrong, right? So same thing, I'm going to start with my single patterns first. So I'm going to start with my the 2 atoms with differing electronegativities. So pattern 4. I'm going to take the electrons that are in this pi bond, I'm going to put them up on that oxygen, and we're going to be left with negative, negative, this guy. We've got a single bond. We've got lone pairs, lone pairs, lone pairs, right? And so now we have a negative, and we have a positive, okay? So same exact thing. We can go through and say, okay, well now we have a positive charge here. We've got a positive charge, we've got a lone pair adjacent to it, just like we did for acetic acid. We can put our electrons there and draw our little resonance arrows. We get a double bond. We get lone pair, we get a single bond, lone pair, lone pair, lone pair, all right? And we'd end up still with our negative charge over here, okay? So now, why am I doing this again? We're still asking who are actually significant structures for this overall molecule. You would think, after drawing these 3, that this guy would also have 3 resonance contributors, resonance contributors, just like what we just drew for acetic acid, but you would be actually incorrect, right? So now again, this goes back to the fact that if we do introduce formal charge, we never want it to go past 2 charges, right? So if we look at we say this is structure 1, this is structure 2, and this is structure 3. If we look at structure 2 at this point, we actually have 1, 2, 3 charges here. And so because of that, this guy is not a resonance contributor, right? If we're going to draw these, we don't ever want to surpass 2 charges. With structure 2, because it has 3 charges overall, so because it has 3 charges, it's not going to actually contribute anything to the overall structure. And so the only 2 resonance structures for this molecule are 1 and 3. Okay. So then if we wanted to list who was most significant, if we look at 1 and 2, so we can go ahead and redraw these. We get our minus here. versus R minus here, these guys don't actually differ with respect to one another, right? So these guys would be equivalent again, right? They both have the negative charge on oxygen, the double bond between carbon and oxygen, so both of these guys would contribute about 50%, and there is no, like, I guess, major contributor, respectively. Okay, so hopefully we're going to finish off this little PowerPoint. So we've been going over kind of like the rules on how to draw resonance structures, and we've shown you these various patterns, right? And so at the end here, we're kind of just talking about stability, right? And which resonance structures are going to contribute more to the overall structure of a molecule. And so we kind of give you two overall like axioms. We say like, oh, well, if you have a positive charge, like if you're introducing a positive formal charge into something, then you want to put it on the least electronegative element. And then conversely, if you have a negative charge, you want to put that on the more electronegative element. But then there's also this idea of, well, if you can complete an octet, you want to complete an octet, right? So, for example, so we have this molecule where we have a positive charge here, right? That's directly adjacent to a lone pair of electrons, right? So this is one of our patterns that we've learned. So this lone pair can go and form a double bond here, and the structure that results from this is this guy, right, where we put the positive charge now on the oxygen. Okay, so the question is, well, of these two, of let's say structure A versus structure B, which one contributes more overall? So in structure A, we've put the positive charge on carbon, and in structure B, we put the positive charge on oxygen, right? So if we're thinking in terms of putting the positive charge on the least electronegative element, ideally that would be best suited to be put on carbon as opposed to oxygen, because oxygen is more electronegative. So you would think, oh, well, structure A is going to be a larger contributor, right? But again, the thing that trumps all of this is octets, right? And so in structure A, we have carbon that lacks an octet, but in structure B, everyone has an octet, right? So even though we have a positive charge on oxygen in structure B, right, and we'd like to put that positive charge on carbon instead, because everyone has an octet in structure B, this guy is going to be a greater contributor, right? So contributor to the overall structure. Again, both of these are going to contribute, right? So we're not like ruling any of these guys out, but structure B is going to contribute more overall than structure A. Same thing with this guy, right? So we've got, we'll call structure A. This is one of our patterns where we have nitrogen, which is fairly electronegative. It's separated, or it is separated from carbon via double bond, right? So one of our patterns is more electronegative atoms taking the pi electrons. So we can draw the resultant structure for this guy. Nitrogen, that's ugly. Nitrogen with the lone pair. Now we have a positive charge on the carbon, right? And so again, these guys differ in the fact that we've got a positive charge on the nitrogen in structure A. Now we've got a positive charge on the carbon in structure B. Again, we want to put that positive on carbon, but for these two, structure A, everyone has an octet, and then in structure B, carbon lacks an octet. So again, structure A is greater than structure B here, even though we do have the positive charge on the more electronegative element. So carbon lacks an octet. Okay, so to kind of end it up, we did these in class, right? So these were 3 molecules, and I wanted you guys to draw the significant resonance structures for them. I'm going to do the easier ones first. So we'll say that this guy is A, this guy is B, and this guy is C. So I'm going to start with B to kind of illustrate what I want to do here. And so I look at this, right? So I look at structure B, and I'm like, okay, what type of patterns can I find? And the only one that really pops to my mind is 2 atoms with differing electronegativities separated by a double bond, right? So we've got oxygen
fairly electronegative, carbon, not so electronegative. So my first structure that I'm going to draw here, I'm going to give the pi electrons to oxygen, which is going to result in this structure. Right, where now those pi electrons have become a lone pair on oxygen. We've still got this double bond, and now we've introduced a positive charge on that carbon. And then from here we have now a positive charge in an allylic position, right? So another structure that we can draw is the electrons in this pi bond going over here. And the resultant structure here is this guy. We still have negative. I should have drawn that up here. Now we've got a double bond here, and the positive charge has moved out to this carbon. Okay, so the question is, are all these significant? And so yes is the answer to that. All of these guys are significant. So all of these would be given resonance structures for this molecule. The more significant one is going to be structure 1 here, right? Because there are no formal charges. Everyone has an octet. Everyone's happy. We have introduced formal charges in 2 and 3. But again, we can do that. That's okay. It's not the worst. It's not the end of the world. If we were going to rank these, structure 1 is much more significant than structure 2 or structure 3, and these guys are probably equal, right? They both have positive charge on carbon, negative charge on oxygen, and yeah, they're both pretty much equal. Okay, so it is okay. Carbon doesn't have an octet. That is okay, right? It's for all of our resonance structures. Structures with carbon lacking an octet are going to still contribute overall to the structure, the overall structure. They will still be significant resonance structures. Okay, so I'm going to move on to C. Again, if I draw on my lone pairs in C, it's not really anything that's obvious, so I'm going to start again with the same thing. Nitrogen and oxygen, or nitrogen carbon, have different electronegativities. They're sharing a pi bond. So we're going to give those pi electrons to nitrogen, and the resultant structure looks something like this. So we've got nitrogen to a hydrogen. Now we have 2 lone pairs. We've given nitrogen a negative charge, and now this carbon has its positive charge. And we still have a double bond here. And so now we've got a double bond in an allylic position, or a positive charge in an allylic position. So another one that we can draw is these guys moving here. And we are left, drew that completely wrong, and we are left with nitrogen to hydrogen, lone pair, negative charge, double bond, and now the positive charge is out here. Okay, so again, all of these 3 are significant. We have introduced charges in this structure, right? And this structure, but again, there are only 2 charges, and they're both -1 and +1, so that's okay. We do have the negative charge on nitrogen here, and the positive charge on carbon, which is good. And even though carbon lacks an octet, that is fine. We can deal with carbon not having an octet. All right, so again, if we were going to label these, this is structure 1, structure 2, structure 3. All of these would be significant, and we'd say probably 1 is greater than 2 and 3. 3 and 2 are pretty much equal. Same thing that we saw for B. Okay, so then A is the next step here. So A is kind of more difficult. I'm going to draw it back out to the side over here. So we're going to start with this guy. We've got a double bond here. We've got a lone pair and a positive charge on oxygen. Okay, so I'm going to start with the same thing that I've started with before, which is this pi bond between 2 atoms with differing electronegativities. I'm going to start with the top oxygen, so this oxygen, and I'm going to go ahead and just give those electrons to this, and we're going to be left with something that looks like this. So we have a double bond to a hydrogen, lone pair positive charge. Now we have a negative charge up here, and we have a positive charge here. Okay, so this is one structure, right? And we've introduced some charges which aren't the best. We don't really like doing that. that may be not so great. So we're going to keep following this. So now we have a positive charge in an allylic position, right? So we can move this guy and be left with something that looks like this. Oxygen, positive. We've got a double bond, this guy. This is negative. And now what we've done here is now oxygen has a 2+ charge, right? And also, most importantly, oxygen lacks an octet, right? Which is a no, right? We can't have oxygen without an octet. Carbon, we can, it's okay, but oxygen, nitrogen, any of those guys cannot not have an octet. So immediately, this kind of stops this. And so that's not going to be a significant resonance structure. If we go back up here, right, and so if we instead had started maybe with this pi bond and the pi bond between these two maybe being different electronegativity, that would have given us a different structure. So let's say that we do that. We're going to give these guys here. And we're going to follow this structure. So now we have a lone pair, a hydrogen, a double bond to an oxygen, and a positive charge here on carbon. Again, we've got a positive charge in an allylic position, right? So another thing that we could do is we could move these electrons down and see what we get as a result. All right, so now we have a double bond, but again, notice that we have an oxygen at this point without an octet, right? So immediately you should be like, no, that can't happen. So no, this is not going to be significant. And so in reality, if we're looking at both of these structures that we ended up with, this guy and this guy, only one of these is actually going to be a contributing structure, right? The problem with this one is that we had overall 3 charges. And we usually don't want to do that, right? So we're okay with 2 charges, but 3 charges is too many. And so I would say probably if we wanted to draw just significant resonance structures, this one probably doesn't contribute, and then we're only left with these guys overall. So again, the question is, well, when do I stop? Well, anytime you start to break these rules, right, where you start to give things less than 8 electrons, or more than 8 electrons, or anything like that, usually that's when you're going to stop, right? It's not going to go anywhere else with that. Okay, so hopefully that makes that a little clearer. Again, what they were looking for here is significant resonance structures, right? And so for the answer for this one is just these two. These guys will not contribute because, again, they break too many of our rules.